Hello, good afternoon, sir,
Good
and good
afternoon.
afternoon, all the participants. Today we start with a session with Dr. Manmohan Das Goel. 1 minute, sir. Hello. Okay. Session is delivered by Dr. Manmohan Das Goel on concrete and other construction materials behavior at varying strain rate. So we welcome you and all the participants. We start with a short brief of the sir. Sir has completed his Bachelor of Engineering from Yashwantrao Chauhan College of Engineering, Nagpur, under the Nagpur University in 2000. He was awarded 3 gold medal by Nagpur University for academic excellence. Upon qualifying through GET in 2001, Sir pursues Master of Technology in Offshore Engineering from Indian Institute of Technology, Bombay in 2003. Sir has completed his PhD from Department of Civil Engineering from IIT Delhi and University of Federal Armed Forces, Munich, Germany under German Academy Exchange Service Sandwich Fellowship in year 2030. Uh, Topic was blast response of structure and its mitigation using advanced lightweight material. Sir has many awards to his credits. He was awarded Sundarnath Mukherjee Memorial Medal for Best Research Paper by Institute of Engineers in year 2009. Sir has been selected Young Ambassador by German Academic Exchange Service for consecutively for 2 years. Sir's thesis has been awarded as the best thesis by Indian National Academy of Engineers under Innovative Student Project Award 2030 at doctorate level in civil engineering discipline. Sir has been awarded CSIR Young Scientist Award 2014 in engineering science by CSIR. So is recipient of Young Engineers Award from Institute of Engineers in 2014. Sir has been nominated at Data Research Ambassador by German Academic Exchange Service. Sir is also recipient of Young Associate Maharashtra Academy of Science Maharashtra in year 2015. Sir has awarded for paper IGS Heiko Benil Award 2017 by Indian Geotechnical Society India as a best paper on rock mechanics published in Indian Geotechnical Journal through Indian Geotechnical Society. Sir has been interviewed by Rajya Sabha TV under popular science program Eureka in recognition of contribution to the R&D in engineering services. Sir has been Senate member of ACSIR Delhi. He is life member of several professional societies. Sir is an active reviewer for many international and national journals. Sir has completed more than 15 R&D projects funded by CSIR, DST, SERB, and DRDO. Sir is associated editor of Practice Periodical on Structural Design and Construction, Journal of American Society of Civil Engineering, and associate editor, Frontier in Building Environment, Computational Method in Structural Engineering. Sir is currently serving as associate professor in Department of Applied Mechanics Applied Mechanics, Vishweshwarya National Institute of Technology, VNIT Nagpur. To he served CSIR Peria. He served as a CSIR AMPR Bhopal and CSIR Niri Nagpur, India as a scientist. So has more than 150 international and national journal conference publication to his credits. He has filed 6 patents. Sir is guiding 8 doctoral research scholar at present. His area of research interests include blast analysis, blast resistant structure, lightweight material, composite structures, low, medium, and high strain rate material, characterization, and computational mechanics. He is looking forward to contribute in the broader area of structural protection system use against blast and impact loading. So I requested you to start with session.
Okay, thank you very much, ma'am. Am I audible?
Yes, sir.
Okay. So, good afternoon, everyone. And the topic, as told by the madam, is concrete and other construction materials behavior at varying strain rates. So, basically, there are two main words written here. One is concrete and construction materials. Another one is strain rate. So, we are going to understand the effect of strain rate on these different materials. So why we need to study this behavior of strain rate? So as a civil engineer, we know we used to perform simple compression or simple tensile tests. Compression test is generally performed on concrete cubes or molds, cubes or cylinder using CTM machine generally as per the respective standards. And tensile test we generally perform on the rebar using UTM. Now in these two tests, the material is loaded at a particular rate of loading. The crosshead or the platons which are moving, these are moving at a particular rate, and then you get the response in the terms of force versus deflection curve or in the terms of stress versus strain curve. Now my question is that when we apply this loading, the rate of loading is very slow. As we increase the rate of loading, let us say I apply a sudden loading, the effect of the material will be different and its behavior will also change. So when you want to design any structure, any facility subjected to high rate of loading, then you have to understand the material behavior at varying strain rates. So this is the topic of today's discussion, and this slide shows you a underground station named Balham Underground Station in London before and after bomb blast in Second World War. So a direct missile was hit, and you can see a bus which was traveling over the road just immediately fell down inside this the metro. So this is a tube metro, and a lot of damage was happened. Many peoples were killed. Similarly, when as all of us know that the Gaza is a very tense area and lot of missiles are fired from other countries simultaneously. So this is a building where this direct missile hit on a building was applied. So in order to design the structures against such kind of effects, the other picture shows you the Alfred Murrah building in Oklahoma State in 1995, which was bombed, and the world famous World Trade Center in 9/11 attack. So whenever there is such kind of things, the structure has to behave in a different way. Since loading is very high and high rate of loading is there, so materials behavior plays a very important role in designing such kind of a facilities. So this kind of disasters, if you use a normal design philosophy, then your structure will become too much bulky. So uh, you have to study the effect of strain rate, which is the ratio of velocity of the crosshead to the length of the sample. So for example, if you are applying a velocity of the crosshead as 1 meters per second and your the sample length is 1 meter, so strain rate will be 1 per second, right? So when we try to find out the strain rate, material behavior definitely changes. So high strain rate value varies from 10 raised to power 2 to 10 raised to power 4 per second basically. And these are important, as I already told you, from construction point of view to in order to design a lightweight structure. Another important uh, requirement of studying this particularly strain rate effect is the proper use of available material model in the computational simulation. Nowadays we know that we are surrounded by the computers and so many softwares are available. For example, STAD is there, SAP is there, Abacus is there, finite element based software, LS Dyna is there, and so forth. So many software exist for civil engineers to carry out their work or research. So in these softwares, many material model exist. Material model is nothing but the stress strain behavior of that particular model. So the basic stress strain behavior which we studied in our undergraduate is sigma is equals to E into epsilon. That means stress is proportional to strain. That is one of the simplest elastic, fully elastic material model. But when you go for analysis or design, there exist many more complex material model which takes into account of many properties of the material. So when we have a prototype structure, we just convert this prototype into a simplified prototype. For example, if we have to model a building, we don't model the doors and windows in the building. We just remove them and we model the frames. So we make a simplified prototype, and from that prototype, simplified prototype, we generate a mathematical model. And then mathematical model is developed, and this mathematical model is later on converted into the finite element models. When we are analyzing finite element models, we need to apply the material properties, like in SAP or STAD or Abacus or some other softwares. You are applying some material properties. That means what is the stress, yield stress of the material, what is the strain of the material, what is the elastic modulus of the material, what is the Poisson's ratio, so and so forth. So this is required to complete the development of finite element model. So when we talk about the development of finite element model, there exist different varieties. So we will be discussing or focusing on the continuum mechanics, which is called as a CM. So this continuum mechanics works on the principle of Newton's second law, force momentum, conservation of energy and mass, then deformation, stress strain displacement relationships, and strength model, which we just discussed. So now when we want to test these materials, then we have to understand what are the equipments available for testing of such kind of a materials to study the strain rate effect. So quasi-static test is those tests which we have performed in our undergraduate, like CTM and UTM test on the concrete and the rebar respectively. And for them, many well-defined model exist. But however, when dynamics is involved, dynamics means rate-dependent loading. That loading is varying with the time. Then it has involvement of strain rate, it has temperature, and as well as pressure effect. So when you talk about dynamic experimentation, the experimental difficulty is significantly increased, right? There is also uncertainties and measurement difficulties involved in dynamic experiments. And as on today, even after the so many years of development of such equipment, the physics and mechanics or mechanism of the material is not well understood. So there exists still a large scope about the behavior of material, particularly under dynamic loading. So if we talk about behavior point of view, material can be classified basically ductile material or brittle material. Like concrete, concrete breaks suddenly, so it is a brittle material. So when you talk about brittle material, strain rate effects on the strength. Strength means the breaking point, like characteristic strength, like for example M30, M40, something like that. Whereas ductile materials like rebars, we have strain rate effects on the flow stress. What is the flow stress? We are going to see in the coming slides. So now when we want to study this, so we can divide whole system of testing in different parts, like creep, quasi-static, impact, blast and shock. So on one type it is strain rate effect, another type is test duration. So shorter the duration of the test, longer is the uh, strain rate, or higher is the strain rate, and vice versa. So when we talk about strain rate, so strain rate phenomena varies from 100 per second to 10,000 per second or even higher. In quasi-static test, we use servo-hydraulic machines, whereas in case of high strain rate test, we can use the equipment listed on this. Among these equipment, one of the equipment which is called as a split-Hopkinson pressure bar is most commonly used, and we will be discussing shock tube test also, right? So now this uh, effect of strain rate when you are designing facilities against such rate of loading like blast, impact, crashworthiness, and high rate phenomena, then you can account these properties into your constitutive model. And this has been permitted by American Society of Civil Engineering through the definition of some of the factors which we will see in the coming slides. So let us first discuss about the split Hopkinson pressure bar. This is a picture of a split Hopkinson pressure bar of one of the European facilities where I worked. And this is the gentleman, Bertram Hopkinson, who developed this split-Hopkinson pressure bar. This bar is used to measure the material strength at high rate of loading. So this is a apparatus which is available at VNIT Nagpur in my lab. So it works on the one-dimensional elastic wave propagation theory, and using this apparatus we can generate the stress strain curve of a material under compression loading. So this is a very big equipment, and we can use this equipment to find out. So just I'll show you some video. Just see, it has striker. Let me just first tell you, the yellow one is striker bar, and just a moment. So yellow one is striker bar and the blue one is your incident bar, whereas transmitted bar is the green one at the end. Between incident and transmitted bar, we will keep the sample as shown here. We will keep the concrete sample or any other material sample. And then once this striker bar is launched, it will hit this end of the incident bar. The wave will travel through this incident bar. It will reach at the interface of incident bar and the specimen, and deformation will happen, and we will capture the transmitted wave also through the transmitter bar using some instrumentation. And then we will use some mathematical formulas to calculate the stress strain curve similar to your UTM, but the loading rate will be very high. So now let us see this video and just have a look on that. So here you can see that deformation of the sample, how it is happening. And we are capturing this kind of signals where my cursor is there. So you can capture these signals and can utilize to development of stress strain curve. Right. So this is the schematic diagram of this whole process. So we can keep sample here. We will measure the incident strain. We will measure the reflected strain. We will measure the transmitted strain. And then using stress strain principle, we will calculate using this one-dimensional wave propagation principle. We will calculate the structural behavior or stress strain curve of these materials. Now, this was little bit about the use of experimental concrete testing at high strain rate. Now these people throughout the world are working in these areas and they have developed some codes or references for this purpose. For example, if we talk about the steel uh, when subjected to high rate of loading, there is a large change in the strength value, which we will see. So these, how to account for these values, you can use these ASTM standards. So here you can see different types of steels and their stress behavior as per the US code. So now when you subject these specimen to high rate of loading, so their strength increases. For example, if we say Fe415, if you subject it to a strain rate of let us say hundreds per second, this Fe415 may reach to up to 700 MPa. Now similarly, M30 concrete when tested at 100 per second strain, it may reach to 90 MPa. So what is the advantage? Why it is not available at quasi-static level? Because in quasi-static region, the molecules does not get the times to readjust themselves, right? They get sufficient time, but in dynamic region, they don't get time and they offer the resistance against deformation, and this resistance results in the increase of dynamic strength. So the ratio of dynamic strength to the static strength is called as a dynamic increase factor, which is generally mentioned in many of the codes, and we apply that. So I will tell you a clause like when you are designing a steel structure, when structure is subjected to earthquake or wind loading, then you generally increases the steel stresses by 1.33 times or 33%. This 33% factor is coming from this kind of a test. So this slide shows you the effect of on the stress with respect to change in strain at room temperature, at minus temperature and higher temperature. So when you are designing any facility, for example, you have to design a component of aircraft, then you have to do this kind of a test and see at varying temperature, at varying strain rate, how the material is behaving. So this is a typical stress strain curve of a high strength steel. So if you see black curve is is the order of quasi-static strain rate, that is 0.005 per second. And if you keep on changing the strain rate, and if you go to, let us say, 1000 per second, then you see your first strength, peak strength, is coming around 1100 MPa. It is oscillating, whereas your quasi-static strength is around 250 MPa. So you can see there is a four-fold jump in the strength. However, the strain is reduced, but that's okay because we need the material to perform or resist this load at very high level rather than this. So similar chart you can develop for the different temperature. So this is the one of the tests which we did in our lab using split Hopkinson power on the aluminum tube. So you just have a look on that and let us see how it is. So this tube will move, left hand side tube will move, and it will fire, right? So this happens in such kind of a test, and then you can generate this type of a stress strain curve. So if you talk about aluminum, aluminum has a yield stress of around less than 200 MPa. When this was subjected to high strain rate, the strain rate was around 175 MPa. This is the strain rate versus time curve, and peak strain rate achieved is around 175 or 180 MPa. Here you see in the second curve. And with respect to this, you are getting a higher strain rate, higher strength of 300 MPa. So similar process can be used for testing of the material at high strain rate. So this is a typical behavior of the concrete. When we have a concrete testing at quasi-static 10 raised to power minus 5, we have a strain rate, we have a strength about this one. This is axial stress, compressive strain, this is tensile strain. So we have a strength test of something like that. And when we test it at high strain rate, let us say 100 per second. So this, for example, this is in Pascal, 5 into 10 raised to power 5 Pascal, and you can say it is 2 into 10 raised to power 5 Pascal. It is reaching up to 1.75 into 10 raised to power 7 Pascals. So you can say there is a sudden increase in the strength of the material at such rate of loading. So one person compiled, Bishop and Perry compiled all these data since beginning of 1917 till 1985, and this data is further improved by many of the researchers. So here you can see, if you calculate the increase in compressive strength, relative increase, that means the dynamic strength divided by the compressive strength in static, will get a factor which is in terms of 1, 1.5, 2 or 2.5. So if you go for 100 per second strain rate, your strength is increasing at least by a factor of 2.25. So this factor or this type of factors can be used in the design of a concrete structure, which is this. So this is another picture of testing of the concrete sample at our lab only in VNIT Nagpur. We have this facility where we can test any of the material under compression. So you just right. So once we tested, we get this kind of, this was a M25 samples having some rubber. So M25 samples shows a strength of 100 MPa. You can see this is the strength behavior, and this is the strain rate. We just tested at 60 per second. So we got a M20, M25 strength goes to 100 MPa at a strain rate of 60 MPa. Now this curve can be used to calculate the energy absorbed by the material in this one. So this typical slide shows you the effect of strain rate which was tested for M25 concrete. So M25 concrete was tested, which is at 0 per second, means quasi-static one, and we keep on changing the strain rate, and we went up to 1000 per second. So you can see this M25 went up to 130 or 150 140 MPa. So it is giving you four-fold increase in the strength, and similar behavior will be observed with respect to FP250, 415, 500, and so on and so forth. So it is not possible for everyone to account for the this kind of a testing. So what people done in the code, they incorporated in terms of some values. So when you talk about values, so these factors will come. So this committee Euro the Baton has included this factor in the terms of a relative strain rate. So they provided this formula. If your strain rate is less than 30 per seconds, then you have this kind of a formula can be used, and you need not to carry out the test. But if it is greater than 30 per second, then you have to use this formula. Although this formula is quite old but still valid, and my suggestion is that if we have new formulas available which has been developed by several researchers, then we should use those formulas instead of sticking to the old formulas. And there exist different relationship in the literature which helps you to calculate the strength of the material if you know the varying strain rate. For example, you are designing a facility or you are designing a crash barrier made of concrete, then you expect that vehicle is hitting at 80 kilometers per hour. You can calculate the total deformation in the sample and strain rate, and then can use that strain rate to calculate the strength of the material. So this kind of a uh, relationship exists which are old, but yes, they will serve as a guide to you people in the beginning. Similarly, we can test the steel rebars to one. So this is a slide which is showing the effect of strain rate on the plastics and ceramics. So you see effect of strain rate is clearly visible. When you don't have any strain rate effect, your strength is very low, and even in the polymers, your strength is increasing with the effect of the consideration of strain rate. Similar behavior is also observed in the ceramics also. Although ceramics has low sensitivity to strain rate, but still some kind of a deformation is observed. Now, this slide shows you the effect, stress strain behavior of a glass sheet under high strain rate, which was tested at the blast impact simulation and testing laboratory at VNIT Nagpur in my lab only. So here you can see there is a glass kept between incident bar and transmitter bar, and we are firing it. So the strain rate observed is order of 400 per second in this one, and let us see this what happens to this, and then using the same equipment we have generated this stress strain curve. Now once we have this stress strain curve, this glass sheet can be designed for a particular impact situation. So let us see this. You see how the glass is breaking and how the bars are moving. I'll play this video once again. So we have recorded at slow motion. So using this photography or some other photography technique, you can also calculate the how the material is getting fractured. Right? Just have a look on that, how this fracture is happening. Right? So you can see. So this kind of work can be done. Now this is a slide which is showing the effect of stress effect of strain rate on the foam material. Foam is generally used in insulation purpose in cold countries also, as well as for some energy absorbing devices, packaging and other things. So that foams is subjected to high rate of loading, and people has worked in that. My PhD itself is on this one. So this is a typical Despande flat foam model available in LS Dyna as well as in Abacus. So using this such kind of a test, you can calculate the stress strain behavior of foam material also. So this is a typical test carried out at VNIT Nagpur in 3D printed form. So one of the our collaborators sent us the 3D printed form, and we did the test at the strain rate of around 400 per second, and its strength, quasi stretching strength was very low, around 5 to 12, 5 to 10 MPa. And once it is subjected to strain rate of 400 per second, and so the strength achieved is around 20 MPa. Let us see how it is behaving. You can see. So this was basically, once again, let us see, the sample is getting completely crushed, and using incident and transmitter bar, we get the stress strain curve of the material. This is metal foam behavior at different types of foams is there. So if you see, it is not always that a material will keep on increasing its strength if you keep on increasing the strain rate. Rather, there exist many materials which may reach up to a limiting value, and then afterwards it was start decreasing in the strength of the material. So this is a material made of aluminum, and it is having cenosphere inside it. Cenosphere is nothing but hollow foam, which is hollow balloons made of silica. So these are inserted in the foam, and then we tested this material at high rate of loading, and we find out that after a strain rate of 900 per second, their strength start decreasing. So you can see that 900, even sorry, after a 750 strain rate, so 900 and 1400 is going lower. Same behavior is observed here also. So we concluded based on this analysis that one has to study a material over a large rate of strain rate or large variation of or wide range of strain rates, so that this is clearly understanding the effect on the material. Now, when we talk about the soil, soil is one of the most important constituent of construction industry. This soil on which every foundation is there, and it is the foundation may be subjected to some dynamic load due to machine movement. So the effect of the soil will also be having the strain rate effect, and this strain rate effect can be investigated using such kind of a behavior. So we can test the soil. So and I'll just go briefly here. So you can calculate rock tunneling quality index using this kind of a formula. And if you have these values, you test them and see what is the effect of strain rate. Because when you are doing tunneling and etc. all other things, then your effect on the material will be different. So here you can see the sand was tested in a SHB by one of the researchers in 1999. He presented these results that when we have this strain rate of 1, 2, 4, 5, 771 and 393, how the axial stress was increasing. So if you see 393 strain at 393 strain rate, your axial stress was around 40, which increases to around 72 at 771 per second, and finally it increases to around 120 at 1245 per second. So the same soil is one, it is behaving differently at different rate of strain. So when you are designing any facility, underground facility like metro tunnels which is going underground, or tunneling, or bunkers or shelters which is subjected to high rate of loading, then you can take this into the account and work upon. So based on that, one person omdivar gives the dynamic increase factor for the sand also. So this is a very gray area, particularly when we talk about the research. And this is typically stress strain response of a clay material, which is available in the literature, right? So again, one thing I would like to tell that a lot of people are studying now rocks behavior under high strain rate of loading, because now in India also lot of mountains are being constructed, lot of bunkers, underground facilities are being constructed. So behavior of these rocks must be known at high rate of loading to design this facility. Otherwise, if you design it by considering only static loading, this will be highly uneconomical. So this is a typical test carried out on the rock samples at our VNIT laboratory in SHPB. Here you can see how this sample is deforming. So here you see the crack is appeared only. Now let us see the dynamic test, another tensile testing, split tensile test. Here you see the sample is completely crushed, and then we can test this material and generate the stress. Now it looks very easy that we are putting some samples between two rods, firing it and doing some test, but it is very complicated. And since SHPV was basically mm, designed for the metallic materials, but nowadays it has been extensively used with certain modifications for non-metallic materials. So many a times the researchers who is not well understanding the basic principle of SHPB, split Hopkinson pressure bar, the data is misinterpreted. And the materials which are typically hydrosensitive materials, they have issues of transition from uniaxial stress to multi-state axials. Whereas in SHPB we always talk about the uniaxial state of stress. So concrete rock polymer ceramics basically are the material which has smaller effect on strength as predicted by the many formulas. So we have to be very careful in this analysis. So once we have this dynamic strength, you can calculate dynamic strain rate, and then dynamic strain rate can be used to stud this. So now there is a code which is called UFC 3340, which gives the dynamic increase factor. If you are not working in the research, you are not doing research, and you want to design these facilities, then you can use the facilities to calculate the dynamic increase factor for the uh, designing this facility. This is similar to the factors which we apply to the load in using IS 456 or IS 800. So These factors are available for every type of action. For example, this is a chart which is adopted from Department of Defense US. So if there are two conditions they have given, low pressure and high pressure conditions, and what is the effect of rebar in yielding, tensile, and as well as concrete is given. So rebar two part is there, yielding and what is the ultimate tensile strength. So if we talk about flexure and flexure yielding, the factor is 1.17. For example, if we have a bar of 250 or 415 MPa and we want to design it for yield, then its strength can be enhanced by a factor of 1.17, whereas in case of tensile it can be increased by just 5%. For compression, it is 1.1 and 1. For shear, distortional and direct, it is 1 and 1.1. For bond, it is 1.17. Whereas if you talk about the concrete, your flexure is having a factor of 1.19, compression is a factor of 1.12, so and so forth. So if one does not have detailed idea, he or she can use this chart to design the facility. But one thing has to understand that since such kind of a facilities are designed for once a hit in lifetime, so you can be little conservative in this designing, because it is very difficult to perceive the threats which is happening or which is going to happening on such kind of a structure. So you can be little conservative in designing the work. So this is the chart which is given in UFC. It says you what are the dynamic design stresses and depending upon the rotations, right? Let us say if we talk about flexural action, we have rebar which can be in tension or which can be in compression, and if dynamic rotation or support rotation is within the 0 to 2%, 0 to 2 degree, then fdy1 will be used and f dash dc will be used. So f dash dc is given in this chart, in this code at the end. So accordingly, you can define that what is the dynamic strength of the rebar, what is the dynamic strength of the concrete, and how it is correlating with the rotations. So if rotations is higher, definitely your strength is going to be lower into the design. So this is the another curve for M50 concrete, right? It is given in terms of dynamic increase factor by European Union, CEB, Committee the Euro Betin, and strain rate effect is given in milli per second. So if you have a strain rate, let us say 0.0002 milli per second, you use a factor of, you read this value and use a factor of 1.21. So this is basically nothing but the representation of Bischoff and Perry's charts on other one. Now let us say if we have a yield strength, which is basically this data is taken from American steel, and for tensile strength of the rebar presented by Malwar in 1998. So grade 40, grade 60, 50, 75, and so on and so forth. So with respect to strain rate up to 100 per second he has given. So you can directly use these charts to find out the dynamic increase factors. Once your dynamic strength is increased, definitely you are going to get a less area of the steel in the one. Now for example, I am a teacher working in some isolated place or some place where this kind of facility is not there, but I have a computer with me, so I can simulate such tests directly. So this is the FE modeling of complete split Hopkinson pressure bar, where one can model the incident bar, transmitter bar, it can model the sample. For example, here the foam sample was modeled by me. This is my PhD work at that time, and I can completely model hair bar, like which is shown in down left side down one, and this is the sample size. So sample size is very small, only uh, four, 14 diameter sample was there. And once you have this one, you run the program, the wave will travel from this end to this end. You will get the collection of reflected strain, you will get the transmitted strain, and using these principles you will get the strain rate time history, you will get the strain time history, and combining these two you can remove this, and combining these two you will get the stress strain versus time history. So if time is removed from epsilon s and sigma s, you will get a curve. So this is a typical curve which we have just seen some slides ago. that one can develop his model, FE model, and can keep on testing. So what is the advantage of doing this? First is that you can reduce the experimental efforts, because here you can run n number of models with varying end conditions, varying materials, varying constitutive laws. You can understand the physics of behavior of material in a better fashion as compared to the experimental test, because experimental tests are very costly and carrying out such one test is very uh, challenging. So you can use this. So we did that and we calculated the complete stress strain behavior of different materials. So this is just some basic of rock and soil mechanics. I will skip because now another part of this study is that shock tube study. So when you have to design a facility against blast or impact, you need to understand the behavior of material under that type of loading, right? So since handling of explosives is not allowed in academia, it is restricted in many of the countries, including India. So we cannot carry out blast test or such kind of a explosive test as of our own. But there exists another mechanism which is called as a shock tube. In shock tube, what we do, we supply a simulated blast. Basically, shock tube is nothing, it is dealing with the compressive air force. So we will have a section which is high in pressure. So this is the typical shock tube which was used by me during my study at Germany. So this shock tube has one section which is called as a high pressure region, and the another one is known as a normal or ambient condition. And in between these two there exists a diaphragm. Diaphragm is nothing but a very thin material, and when we suddenly suck out the air between these two sections, there are two diaphragm basically. So this there is a low pressure region between these two diaphragm, and this high pressure region, air is forced towards this, it breaks the diaphragm, rupture the second diaphragm, and then a shock will travel. So discontinuity is generated basically in this, and this discontinuity will travel through down through a long tube which you can see, and will hit the material. So this is, let us see just how this is shock tube facility at Sandia National Laboratory, how this material is tested. So it is fired now, you can see, and the compressed air is coming from outside. Now it is showing extreme blast environment simulations. So here you can see shock wave is traveling. We have put a pressure gauges and now it's getting it. So here shock tube is moving. How the shock is moving. And this is a sudden rise in the pressure. At this location we have kept the testing material or testing gauge. So that's why we are observing a sudden rise in the pressure. It is moving. Second gauge is there now. Third gauge is there at the exit. And now you can see how waves is coming out. So this is a velocity of wave which is measured. Here you can see. So using such kind of a testing system, you can exactly play with the material. You can understand whether my material is going to sustain such kind of loading or not. These are very small scale equipments as compared to your real time structure, but these equipments helps you to understand the behavior of material at that rate of loading. For example, let us say we have a nuclear containment structure and a plane is striking. Another example is WTC. So now can I design my structure, which is very important, that even if a missile or plane directly hits this structure, then nothing should happen to the structure. Like any containment structure, nuclear containment structure is housing radioactive material. If that is leaked, then lot of people will die. So such kind of a structures are designed made of concrete, and these are designed using such kind of a facility only. Right. So I was talking about the high pressure region and low pressure region, which is you can see here. So we have a high pressure region, which is this one, and low pressure region, which is this one, which is separated by this diaphragm. So we have this region filled with any gas. It can be compressed air, it can be helium, or so and so forth. So once this is filled, so this is charged region, and this is uncharged region, so low pressure region. We suddenly suck the volume or vacuum out of this using some mechanism, and then this diaphragm breaks out. Once this diaphragm breaks out, the shock travels down this line, and you have this shock wave phenomena directly hitting to the sample, which is kept at the end of this tube, and then you will get the reflections. So all these things can be captured if you employ certain kind of a this sensor. So this is a typical cutout diagram or schematic diagram of the test which we carried out at University of Federal Armed Forces Munich. So this is end section of the tube where samples were kept, and this is the schematic diagram. Here you can see we have arrangement for holding the pressure sensors as well as the high speed camera. So you can insert camera here, and this camera will record the deformation behavior of this material, which will help you to understand the failure of material at that rate of loading. So here shock will come, it will get impacted to the material will deform. You can capture all this deformation and then can later on analyze the structure. So this is a data acquisition system which was used. So here you can see we have a oscilloscope, we have a amplifier, we have a pressure sensor gauges, and complete data cables or attachment to fire the shock tube. Now this is typical diaphragms which were used. So these diaphragms are made of mild steel as well as the uh, copper. So we do marking, and since this marking reduces the overall thickness of this diaphragm at that particular location, so they open in this. So in above picture you can see cross mark are there on both aluminum as well as copper one. So this you can see 1.4 mm thick mild steel sheet is there, and 1.4 mm thick, around 1.3 or 1 mm thick is copper one is there. So we fired this, and this does not open fully. So here in down line left side down image you can see it was deformed, but it was not opened fully. So that's why shock could not travel to the other end. Same thing happened with this one. We tried several combination, and finally we were able to. Sometimes it was partially opened here where you can see my cursor is there, and at the end finally we were able to achieve that how it shall open. So it opened like a flower petal. So once this is opened like this, so full shock wave will travel to the end, or which is called as a planar shock wave. So we tested so many combination of these one and then optimize the uh, opening of diaphragm. So these are typical metal foam samples which were tested. Metal foam is nothing but it is made of aluminum. Like we have all the utensils made of aluminum. So when we foam it, it becomes metal foam. And you will be surprised to know that the density of this metal foam is only 200 grams per or 200 kg per meter cube, right? So it can float on water, but the property is that it absorbs large amount of energy. So when you compress this, the layer wise deformation happen in such materials, and they absorb large amount of energy. So they can be used as a sacrificial layer in terms of protection of the structure against blast or impact. So that helps you to understand the mechanics of the energy absorption. Similar, you can make samples of concrete, or you can make samples of polymeric materials, You can make samples of any steel plates also, how it is going to deform under such kind of loading. So this is the situation of samples before and after test. So we did this test in the shock tube, and the samples were placed, it was fired, and loading was applied. So here you can see how the samples were completely crushed. So once this is crushed, it will get reflected also back to the shock tube, and we have pressure sensors or gauges located at different locations. Using those pressure gauges and sensors, we collect the data and see how much amount of energy is absorbed. And the interesting part of this was that till before this test, we were understanding that all of these samples will absorb the energy. They will not cause the enhancement in the incoming energy. But many times when we did this test, it was surprised to know that at particular level of loading, they were causing the enhancement of the reflection rather than the reduction in the loading. So that was a very interesting point, and that led to understanding of importance of such kind of a test in the one. So these are the foam samples which were before and after deformations or partially deformed. Here you can see the thickness of the sample was 50 mm, and finally it was reduced less than 1 centimeter after the test. So layer wise deformation was observed and complete deformation. So here you see whatever the pressures versus time curve we got, we have an incident pressure as well as a reflected pressure for two sensors, and for different density of foam we get it. So here we can see that some of the uh, pressures were higher, some of the lower, and with different types of foam we were able to calibrate the data on the behavior of the material. So now this was about the metal foam. Now coming back to the shock loading on soil, we have, if we have this kind of a behavior which is showing the shock velocity versus particle velocity, if you keep on increasing the velocity, particle velocity or shock velocity will also increase. And if you have a varying density of the sand, like sand, soil, silt, and sand quartz sands, their behavior is also different. So all this data is basically required when you want to use this data for modeling. Where to model? Like in SAP, in Abacus, or anything. So that is required to be used in constitutive model. So whether you are going to use cell elements, solid elements, whether you are going to make beam column connections, so you can use this test data to model the material behavior at that rate of loading. For example, let us say I have a building which is going to be subjected to some kind of a missile attack. So now I must know the what are the types of material to be used in that one, what is the behavior of that material at that rate of loading, and how to diffuse this. So combining all these things can be achieved with doing some test on either using SHPB or shock tube and developing such kind of a relationships. So this is a very important relationship, particularly for the structural steel, which is called as a Johnson-Cook material model, that sigma equals to sigma 0 plus a epsilon raised to power n 1 plus b epsilon epsilon dot upon epsilon 0 1 minus t raised to power b. So it is having three parts. One is your elastic plastic part, which generally we study in structural engineering. Second part is strain rate, which we talked today, and third part is temperature. And the beauty of this model is that even if you remove one part, let us say I did not carried out temperature study, I did not subjected my samples on higher temperature, then I can remove this part and still this formula work. Next part, if I don't have temperature as well as strain rate effect, then I can remove last two terms and I can work with elastic plastic material, which is a very important one. So this kind of work can be carried out, and if you don't have anything, you just adopt the dynamic increase factor. For example, the Department of Defense is giving for different US steel. For Indian steel, it is still not available because nobody has worked one. But for other steel, ASTM grade steel A36, 584, 588, 514, and depending upon their minimum yield strength in KSI, kilo square per inch. So it is given that if it is in flexure, low pressure region, high pressure region, then use these factors. Similarly, for axial, low pressure and high pressure region in one, and for tensile strength, what is the dynamic increase factor? You see, the increase factor is very small given here because the uncertainty involved in such kind of a testing. But When you are going to design this facility nowadays, we can do a real test and can arrive our own data rather than, because this factor will be at least 2 in most of the cases. So you can use this kind of a analysis into the design. Okay, so this is a typical real-time test carried out on the steel column as well as RC building. So it was a composite building. You can see some blast test was carried out in one of the test facilities. It has column made of I sections and structures made of concrete. Blast was carried out and it was seen how the column is getting deformed. So here you can see at the bottom what is the deformation in the column, how it is bending, and then it was analyzed to understand the effect of strain rate. So I think that's all for me today because I try to cover the basic ideas of this one. I think I'm quite ahead of the time and I'll be happy to discuss with you people if you have any specific queries. Thank you very much.
Okay. Anyone having doubts related with this? Participants? Anyone having doubts? Okay. Thank you, sir.
Yes, thank you very
If
much.
anyone,
And I understand that this is a topic which is little offbeat for you people, but at just having a basic understanding of that there exists such kind of a phenomena in material, uh, at least you will be aware that what is going to happen if you design facilities under such kind of a loading, which is the future of design.
thank you, sir. Thank you.
Thank you very much. Thank you.
Thank you.
Shall I close it?
Yes, sir. Yes, sir.
Okay. Thank you very much.
Thank you.